Well, thank you very much for the invitation to come and give this presentation. I was very honored when I got this invitation, and it has been a very interesting exercise to try and go through the literature that has been influenced by Cox's paper. Now, the paper has more than 24,000 citations, and I have to make a confession that I didn't read it all. But based on what I did read, this is the way that I have scheduled to make my talk. I will start by making a brief review of the contents of the paper for those of you who didn't read it. I think that out of those 24,000 individuals, at least who have quoted it, I think that only a minority have actually read it. I guess this is not the case for the audience today, but just in case, I will go briefly through it. And then, when it comes to the influence of the paper, I've tried to divide that into three subsections. One, dealing with the short-term influence on the statistical literature. The paper contains so many new ideas that it took the statistical community at least a decade to grasp what was actually going on. And I'll try to review that early literature. Then there's an influence on the paper not only on the statistical literature, but also on the medical literature. And I'll say a few words about that before I turn to what I would call the long-term influence of the paper. And that again I divided into three sections because obviously the paper has had some influence in survival analysis, which is the area in which the paper was sort of conceived. But it turns out that actually new interesting research areas have come out of this paper by David Cox, the concepts of partial likelihood and semi-parametric inference, and I'll say a bit about those two topics as well. So, to the paper itself, it deals with survival analysis, so T is the failure time, lambda T is the hazard function. And it's remarkable to know that already when the hazard function is introduced in the first place, it's acknowledged that not only can the distribution of T have absolutely continuous components, but also discrete components are allowed in the distribution. Then there are the explanatory variables, or the further measured variables, or as they are called in one of the sections. And the idea is then to make inference on the conditional distribution of T given Z. And this is the famous expression for the hazard function. It's a multiplicative expression. We have a baseline hazard for individuals with covariates equal to 0, and we have then the factor e to the beta z, modifying this baseline hazard according to covariate z. And again, some side remarks in the paper are quite interesting. From the very formulation of the model, it was said that z may depend on time, which is actually quite a new and unusual thing as well. And this exponential function could be anything. That could just be some function of covariates and regression coefficients. But the basic idea is that the regression coefficient are the effects of the covariates. It's a parametric part of the model, whereas the baseline lambda 0 is left completely unspecified. And then inference in the model proceeded as follows. It was argued that when you don't specify anything about the baseline hazard, then you shouldn't be able to learn anything about differences between individuals in areas where nothing is happening. So all inference on the betas will happen at the times where a failure is observed. So T1 up to Tk are the distinct observed failure times. And then conditional on who is at risk at a given failure time Ti, this factor is then the conditional probability that it is individual I who fails, given that one individual in the risk set fails. And then these contributions are multiplied together by an argument which was debated quite a lot in the years to come. I should mention that this is how inference takes place in continuous time. In discrete time, a logistic extension of the model was suggested. Then there's an estimator also for the baseline hazard function, or rather for the survival function corresponding to the baseline hazard function. There's an example in the paper taking a data set by Freyreich et al., which had been used already by several authors for illustrating methodological points in survival analysis, and it has been used several times ever since. An interesting thing to notice is that this is in a way not a very good example, because they're used as a standard set of survival data. But if you go back to the original sources of that paper, the data are in fact paired. It's a 2-arm clinical trial, maintenance therapy in leukemia, but for every actively treated individual, there's a matched placebo-treated individual. And that matching is rarely acknowledged in analyses of the data. And furthermore, the trial was sequential. So the fact that people find significant differences between the treatment groups when they analyze the data is not a surprise, because that's why the trial was stopped. But anyway, it was used in this paper, and it has been used before and has been used ever since. So this is quite an interesting data set. And then in the paper, there's a test for the assumption of proportional hazards, an interaction between time and covariate. And actually, the fitting of this semi-parametric model is also compared to some parametric models where the baseline is either assumed to be piecewise constant or a Weibull form. And then there's a small section towards the end of the paper, the discussion section, discussing the physical interpretation of the model. And it's said in the opening of that discussion section that it was put there to please one of the referees, because it seemed that it wasn't there in the first version. But one referee had obviously asked for some discussion of the physical interpretation of the model. And I think it's admitted in the paper that there is no such physical interpretation. And this is a quote, it's intended as a convenient, flexible, and yet entirely empirical model. Whereas the accelerated failure time model with which it's then discussed compared in this discussion section actually does have some physical interpretation. And then there's a discussion about half of those pages is the paper, and the other half is the discussion. And the discussion has actually also been quoted quite a lot ever since. And a contribution by Downton on matched pairs, one on Breslow on estimating the baseline hazard, and one by Kalfleisch and Prentice discussing the likelihood that was set up in the paper. So that was very briefly what's in the paper. And then to the short-term influence of it in the statistical literature. And as I said, there are so many new ideas that are presented in this paper that it took the statistical community at least a decade to comprehend them. And here are some of the early papers that were influenced by Cox's paper and which took up different aspects of the paper. First of all, there was this likelihood construction. And a follow-up on their discussion of the paper, Kalfleisch and Prentice presented some ideas in a biometric paper about how the likelihood could be derived not as a conditional likelihood, but actually as the marginal likelihood of the ranks under certain circumstances when there are no ties and no time-dependent covariates and so on. Also a paper by Crowley on the relationship between the Cox model and the log-rank test. And then there's Cox's paper following up the earlier one, where the concept of partial likelihood was introduced. And then some local, that is Danish contributions. Søren Johansen and Martin Jacobsen had some papers in International Statistical Review, also inspired by Cox's paper. Søren Johansen derived the Cox likelihood as a profile likelihood, which I think is still my favorite argument for how to obtain this likelihood function. And Martin Jacobsen had a paper on extensions of the model, which were perhaps more satisfactory when there were discrete components in the data. Then there's the semi-parametric nature of the model. The baseline was assumed to be just a positive function. And an obvious question to ask, and that was also asked in the original paper, is then how much do you lose when you don't make any assumptions about the shape of the baseline? And there were some papers by Efron and Oakes discussing how the efficiency was for the partial likelihood estimator compared to models where the baseline has a parametric specification. And then finally, this unusual likelihood and the semi-parametric nature of the model and censoring, that gave room for studying asymptotic properties of the model. And the first paper on that was by Ziatis in Annals of Statistics in 81, using classical empirical process theory. Later there were some papers using martingale arguments, but basically arriving at the same asymptotic results. So that was very briefly on the sort of the short-term influence of the paper. Then, if you look at those citations, and as I said, I haven't looked at all of them, but when you look at them, you certainly get the impression that most of them come from the medical field. I would say that maybe 90% of the citations of Cox's paper are from medical journals. And the Cox model has indeed become the standard tool for regression analysis of failure time data in medical applications. And actually in the first years where it was possible to do the analysis, the word Cox turned into a verb. Medical doctors came to our department and said that they would like to have their data coxed. They don't do that anymore because now they can do it themselves. Lots of flexible software is available, and that certainly hasn't decreased the speed with which the paper is being cited. But if you look at those applications, and I've looked at some of them, you get the impression that some of these analyses presented in the medical papers could have been conducted more carefully than they seem to have been conducted. And various aspects of the model is not even touched upon in these papers. Maybe because they didn't want to spend precious journal space on discussing these problems, but maybe because they didn't pay too much attention to it. And among these problems which are not discussed are: how well does the model fit? How is the proportional hazard assumption? Is it reasonable or is it not? If you have quantitative covariates, which you often have, there is an assumption of linear effects on some suitable scale. Is that reasonable? Sometimes the model is fitted to very small data sets, and one could question about whether the asymptotic results that are used for inference are at all valid. And one could ask, does it matter, or is the model so flexible that it's capable of handling all those problems without really fitting too well? And I have some example illustrating this. It's not a very good example, but perhaps it illustrates some of the points. It's a small data set which we used in our book on counting processes. It's about 200 patients with skin cancer, and they all got the same treatment. They had a radical surgery performed, so there's no treatment variables in this particular study. Among the 205 patients, there were 57 who died from the disease. Some died from other causes, and the rest were censored when the study closed. And since there's no treatment variable, the purpose is simply to study how do prognostic factors affect the survival time for these patients. And among the variables that we will look at is the sex of the patient, tumor thickness, and ulceration. So let's now pretend that we're interested in looking at the effect of sex. And all studies in melanoma point to the fact that males have a worse prognosis than females. But on the other hand, that may be due to the fact that the males are diagnosed later. Maybe they spend less time before the mirror and find strange things happening to their body. But it's a fact that the disease is more advanced when it's diagnosed. And among the factors that say something about how far advanced the disease is the thickness of the tumor, and also this binary factor alteration. And here we've just fitted a simple model, a linear effect of thickness, a proportional hazards model, This is alteration, and this is the sex variable. So we can see from the estimates and the standard errors that the last two variables are highly significant. Sex is not, but the estimate for the male to female rate ratio is about 1.6, which is the exponential of that one, and I should have put it on the slide, but I forgot. And the question is then, when we look more carefully on how well these other variables are modeled, that is thickness and alteration, how does that alter the way in which we evaluate the differences between males and females? And here are some examples of that. If we add some splines to the model, some linear splines, they turned out to be close to significant. So the log linear effect of the tumor thickness is not really a very good modeling assumption. It seems to be rather some concave functions that models the dose-response relationship. And if we allow for that by replacing the linear effect of tumor thickness by some favorite concave function like the log, we can see that we no longer need the splines, the linear splines on the log scale. They can easily be tested away, and we're left with a model where the rate ratio for sex is now 1.5. So changing how well the modeling assumptions were fulfilled for tumor thickness has changed this rate ratio a little bit. If we then turn to the other factor, alteration, it's binary variable, and one can look, for instance, as how well the proportional hazards model fit for that variable. And if we follow the approach from Cox's paper, we add an interaction between alteration and time, and we can see that it's quite highly significant. So the assumption of proportional hazards for alteration doesn't fit very well. One way of repairing that is to stratify by alteration, and we can see that now the sex effect is 0.36, and the rate ratio corresponding to that is about 1.4. And we can even remove it if you want, but that's not the point of today's presentation. So you can see that these two strongly prognostic factors, thickness and alteration, the way in which these confounders affect the outcome, that has some consequences on how our variable of interest, namely sex, is evaluated. It's not significant in any of the models, and that makes the example perhaps a bit less interesting. But I think it does illustrate that yes, it may matter how well the model fits when you're going to evaluate the results from your analysis. Okay, these are the cumulative baseline hazards in the final model, and we can see what's wrong with the proportional hazards assumption. Those without alteration, they don't die for the first 2 years, whereas those with alteration do. So it's early on that this non-proportionality is most pronounced. Anyway, let me turn to the long-term influence of the paper. And since the paper deals with survival data, there has obviously been an influence on survival analysis and more general event history analysis. And I'll illustrate that with some examples taken from various branches within event history analysis. You can look at multi-state models, that is, models with more intermediate states, and where you can be interested in transition intensities between these various states. One such simple model is the competing risk model, and already in the papers by Kalfleisch and Prentice and others, and in the book by Kalfleisch and Prentice, Cox models were set up for these cause-specific hazards. So already at that time, that was sort of the natural way to approach this new problem of competing risks. And one way of analyzing competing risks is to analyze these cause-specific hazards, and that's a rather sort of direct application of the Cox model. But you can also be interested in what's called the cumulative incidence function. That is the probability QH of having failed from cause H before time T. This is a function of all the cause-specific hazards in the model. So if you fit, say, Cox models to each of the cause-specific hazards, then the plug-in estimator for the cumulative incidence will then be a complicated function of the covariates. And some attempts have been made to directly model how the cumulative incidence is affected by the covariates. So some relationship between the cumulative incidence and the covariates was needed, and surprise, surprise, the model that was attempted, this is Fine and Gray's paper in JASA in 1999, was a multiplicative model with an unspecified baseline and e to the beta set as the link to the covariates. You have to do that in the proper scale, and here it's what would be the cumulative hazard scale if this was a survival function. But again, a new parameter was the object of regression analysis, and the first choice made by these authors was the multiplicative structure from the Cox model. If you look at recurrent events, you can of course analyze the hazard of renewals using standard hazard models like the Cox model. You can also look at models for the mean number of events. And there's a book by Cook and Lawless dealing with analysis of recurrent events. So one of their favorites models is this model, mu t given z. That's the mean number of events in the interval from 0 to t. And in order to model that as a function of a covariate, that was the link that was chosen, a baseline mean number of events times e to the beta set. So the e to the betas are now ratios between mean numbers of events. And let me jump to this one. When patients are treated, the costs for treatment will accumulate over time. And one can be interested in comparing these cumulative costs between treatment groups. And since the costs increase with time, you can think of it as some transformation of a survival time. So attempts have been made to use survival time methods for analyzing censored medical costs. And some papers by Daniel Lin work in that area. There are some problems in that area because dependent censoring makes the estimation a bit more tricky, but this is the basic model. The costs accumulated at time t is assumed to be baseline costs for standard conditions set equal to 0, and then times e to the beta set. So again, a new area within event history analysis was the object of the regression. Everybody's first choice is this multiplicative structure. Other problems could be looked at. Covariate measurement errors. There's a book by Carrot, Rupert, and colleagues. They also have a section on measurement errors in survival analysis. And what they focus on is, of course, the Cox model. In a way, this is not the most neat way to do it, because when you add measurement errors to the covariates, then the multiplicative structure is sort of destroyed. Whereas if one had stuck to an additive hazard model, then that additive structure would have been preserved even in the presence of measurement errors. But in spite of that, the Cox model was the choice for looking at this problem. And the same holds for random effects models or frailty models. As a recent book by Duchateau and Jensen from Belgium came out in Springer 2 years ago. Again, they focus on multiplicative hazard models, so they add a frailty factor to the hazard model, the random effect W. And again, when you integrate out W, then typically you will lose the proportional hazards assumption. Whereas had they started with an additive hazard model, then much more of that structure would have been preserved even after integrating out the frailty. But the Cox model is always the first choice. And another remark to make is that this semi-parametric structure of the model has sort of de-emphasized the use of parametric models in survival analysis. So everyone who does survival analysis does non-parametric or semi-parametric inference. There are exceptions. Lawless's book from 2002 has quite a substantial section on parametric models. And also some other recent books pay more attention to additive hazard models. The book by Martinussen and Scheike and that by Olin, Borken, and Jessing both from Springer are treating additive models in quite a detail. Let me then finish by saying a few words about these two other completely new areas that came out of the 72 papers. One area is partial likelihood. If you Google it, you get 3.7 million hits. And this idea that's behind the partial likelihood construction, that you have a likelihood, you factorize it in a certain way, and then you try to figure out which of the factors are really those who have the information and the parameters that you want to interest, and then you focus on the product of those factors. That's a very brief introduction to partial likelihoods. And that has become a research area on its own. Cox's paper, including discussion, was about 35 pages. Wang wrote a paper in Annals of Statistics, a 35-page Annals paper, dealing only with partial likelihoods, with asymptotic theory for general partial likelihood estimation. There are some papers in Scandinavian Journal of Statistics, one by Erik Slot, who discusses partial likelihood for continuous time stochastic processes, and Richard Gill has a paper which is behind some of the work on frailty models, where he looks at marginal partial likelihoods. The problem is that when you have the frailty and you have a partial likelihood, then you want to integrate out the frailty. But if you only have a partial likelihood, then you have left out some of the factors, and it's not clear that you still get a marginal probability when you do that. And Gill then discusses when this process of taking marginal partial likelihoods, when that gives you something sensible. And then there's a whole other area in epidemiology. The Cox model has also penetrated epidemiology. And one of the trends in epidemiology is that larger and larger cohorts are being analyzed now. If you want to analyze those big cohorts using the Cox model, then you have some work to do, because you need, in all the analysis, to keep track of the whole risk set. And if you have a million person cohort, then you have to keep track of those risk sets, which are roughly of the order of magnitude of 1 million. So sampling from the cohort has become an important trick in epidemiology. And there's an Annals paper by Borgen, Goldstein, and Langholz which discusses that. And they use partial likelihoods to make inference on parameters for sample cohort data. So the idea is that they have a counting process that not only counts failures for individual I, but it also has a mark R, which is the sort of control set that is selected from the risk set at time t. So that process has an intensity process, which, if the basic cohort has a Cox model structure, then you have to multiply this probability that, given the past, what is the probability that you sample exactly the set R as the control set, given that I has to be in the set. And they can set up a partial likelihood for the beta parameters, and they're actually able to treat quite general sampling patterns in that way. And finally, the other new field of interest that has come out of the Cox model is the semi-parametric modeling. If you run a Google fight between semi-parametric and partial likelihood, then the semi-parametric will lose. There's only about 630,000 hits. But still, semi-parametric inference has become a whole new area of research. One of the key persons in that research is John Wellner from Seattle. And here are some of the earlier and some later work by Wellner and colleagues discussing semi-parametric models. So the idea is that you have this structure of the parameter space where it's a product of a finite dimensional vector space, that's the beta parameters, and then some function space, including the baseline hazard. And lots of interesting mathematics has been applied in this area, like differentiability issues in function spaces and things like that. And this is not really my area of research, but I think that it's interesting that this whole new development has happened, also inspired by Cox's paper. So this is the last slide, and it just repeats what I've already tried to say. I think this is one of the most influential statistical papers ever. I don't have a recognition of the history centuries back, but so I'm probably wrong. But it's certainly a very influential paper. It's interesting to see that it has both influenced the statistical and the medical literature. And also I think it's interesting to note that within the statistical literature, not only survival analysis, which is the area of the paper itself, but also these new branches of partial likelihood and semi-parametric inference have developed from Cox's paper. And finally, as I tried to illustrate, this semi-parametric multiplicative model has really set the standards for many other applications within survival analysis and event history analysis. So, thanks for your attention.
Well, first of all, I'd like to thank the organisers for the opportunity to speak on the EM algorithm. I'm always happy to talk about it because I've been a great admirer of it, and so in that sense you're going to get sort of a biased view of it, because I've been fooling around for years with mixture models and latent variable models, and that's an area where the EM algorithm is very usefully employed. It greatly simplifies things. And
I don't know how to make this full screen, Geoff. PowerPoint.
So, okay. So the EM algorithm, well, I think as everyone would know, the E stands for expectation and the M for maximization. And this paper was read to the Royal Statistical Society in 1976 and then published in Series B in 77. And since that time, the EM has become a standard piece in the statistician's repertoire. And in this seminal paper, the ideas were synthesized, a theory developed, and there were a host of traditional examples. Okay, so we need the EM algorithm in situations where we can't write down the maximum likelihood estimate in closed form. It has to be computed iteratively, and the EM does that by alternating these E and M steps. So it's so called the EM because it's got this E step followed by a maximization step, and this is taken from the abstract of the paper. So Dempster, Laird and Rubin were forthright in their opinion about this algorithm, and I think 33 years later now, almost 33 years later, I think most people would agree with their assertion about this algorithm. Now, the outline of the talk, I'm just going to give a brief definition of the EM, look at perhaps some history before it, and then some comments on the impact of it. So the notation, we go out and we've got lots of observations, or hopefully we got a lot, and we put them all into one vector, which I'm going to call Y, the observed data vector, and basically we're not going to actually work with the likelihood function here, the one that we should be working with, because it's it's too difficult perhaps, or in some cases we can't actually write down the likelihood function. And but the idea is if we could only observe some extra variables, then the problem would become simpler, and so that we sort of think of this vector Y, the observed data vector, as being sort of incomplete, because we're going to augment it with some additional data to get a a complete data vector. So we want to perform maximum likelihood estimation. As I say, we're not going to work directly with the likelihood function based on the observed data. We're going to use the so-called complete data log likelihood, and the subscript C here stands for the fact that we're working with the complete data vector. And in many situations, the complete data vector can be split up into two subvectors: the observed vector plus some unobservable data. This is, if you like, the missing data vector. Not always can we write it like that, but that's not a problem. And so if we want to formally talk about this, I won't go through this. We've got a many-to-one mapping from the sample space of the complete data vector to the sample space of the incomplete data vector. But I notice on this slide that my script X and script Y has disappeared. It's come out like this, but anyway, I don't want to. So okay, we've chosen some data to try and make the likelihood easier to work with for the complete data log likelihood, and but we can't really work with it in the sense that this X is not fully observable. So we handle that by the E step, and we have to proceed iteratively. So on the k plus 1 iteration, what we do is we average this complete data log. We take the average of this complete data log likelihood, and we average over all the unobservable random variables, but we condition on the observed data vector, y. So, and in order to take that expectation, we need a value for the parameter vector, the unknown parameter vector theta, and so we use the estimate that we got from the last iteration. And this notation here means we're taking the expectation using this value here for the parameter vector. I could actually write this over here after the condition sign, but so this is the E step. We've got our Q function, and then having got that, we globally, the M step is to globally maximize this over theta. Now, when you're dealing with mixture models with IID data, this E step is basically trivial because this is a linear function of the missing data, if you like, the group labels. Of course, in other problems, this E step could present some difficulties, and one may say there's a stochastic EM where you take one random draw, or you've got a Monte Carlo EM where you take more than one draw, and this of course raises questions of the link between the EM and iterative simulation methods that people have been using more recently, but I'm not going into that today. So that basically is the EM algorithm. We've got these two steps, the E and the M, and we just alternate them until convergence. And so here we've got this monotone convergence. After each EM iteration, the likelihood function, that's the incomplete data likelihood function, the one that we really should be working with, it's not decreased. So if we've got a sequence of likelihood values bounded above, we'll get convergence. And Dempster, Led and Rubin had a slight mistake in their paper, and Geoff Wu wrote a very nice paper on that, just clarifying the issue about convergence. So how does the EM tie in with intuition? Well, it ties in very well. If we had to work with this log likelihood function here, and we didn't know this U, what we would go about it, perhaps we'd have a stab at what the value for U is, use some ad hoc procedure and plug in a value, and then we would get an estimate of theta 1, say, by consideration of this function, maximising it, and then having done that, we'd use this value to update U, and then and so on. And this iterative procedure corresponds to an EM process if this log density, or the log likelihood function, is linear in the missing vector, and and provided we update this missing vector by taking its conditional expectation. Of course, in many applications, we don't take this expectation, particularly in classification problems. We would use sort of outright allocation rather than using this soft allocation. And that, of course, can lead to inconsistent estimates of the parameters. And then there's a generalized EM where one doesn't where one doesn't have to really globally maximize over this theta to ensure monotone convergence. We just want to make sure that this Q function, when we plug in the updated value for theta, it's greater than when we had the previous value. Now, there were many discussants of this paper by Dempster, Laird and Rubin. The proposer of the vote of thanks was the late Martin Beale, and John Nelder was the seconder. And some of these people are here today, and I noticed the people from Scotland were out in force at this meeting. And there were many serious comments, but one comment I liked was from, I think it's Ben Torsney, who said, on the question of naming the author's technique, north of the border, we would be content to describe it as a wee gem, which is not bad because this is a generalised EM algorithm. Now, in other written comments, there was Hartley, who had done work on this back in 1958. So he says, I feel like the old minstrel who's been singing his song for 18 years. So if you add 18 onto 58, you get the 76. He's been singing his song for 18 years and now finds with considerable satisfaction that his folklore is the theme of an overpowering symphony. And then he goes on about using the word score and using it in the Fisherian sense. So, as I said, there are other discussants, and Brad Efron was there, and taking up this about the score, he pointed out that this identity here, which is needed in improving, working out results of convergence, that this was known to Fisher back in 1925 in the context of looking at inefficient statistics. Like a lot of things in statistics, they were known to Fisher. Now Little, who was a student of did his PhD under Beale, said in his discussion, finally I'd like to add to the author's impressive list of applications, and my name gets a mention, albeit not spelt correctly, but this paper never got many citations, and of course it got one less with the misspelling. But in this paper in JASA in 75, I was interested in trying to improve the performance of a discriminant rule when you have a partially classified sample. So you proceed iteratively, but the missing data vector, I'm calling it Z now, previously I had U, it was getting updated using outright allocation rather than soft allocation, and if you didn't have a zero cutoff point, then you'd get you get biased estimates of the parameters. If you use a zero cutoff point, they disappear as long as you can get the sign correct. But as I say, there was, and this paper here was an attempt to use fractional weights, but it was based on large sample results. And of course, once the EM algorithm came out saying that you should actually use soft allocation, then there's no need for those papers. So basically, during the iterative procedure, one shouldn't be assigning the things outright, these observations to the various groups. One should be using fractional weights given by these posterior probabilities. So this is just the posterior probability that the jth entity belongs to the ith component of the mixture given yj. And using Bayes' theorem, if you're fitting normal components, this is the multivariate normal distribution with a mean mu sub I and a covariance matrix sigma sub I. So I know I've rushed over that very much, but the key thing is you have to use this soft allocation during the iterative procedure. And the EM algorithm sort of spelt that out very clearly. Now, while I'm on mixture distributions, there was quite a bit of activity in the 60s about fitting mixture models, and this is a very nice paper written by Nick Day when he was in Australia. these people were astute enough to manipulate the likelihood equations into the form given by the EM algorithm. And they then suggested solving them, as you would in EM, and they noted that the likelihood did increase after each iteration, but they weren't able to prove that it would happen in general. And of course, when the Dempster-led ribbon paper came along, then I think it really spurred a lot of activities in mixture models. Because as I said at the outset of the talk, this is an area where the EM really simplifies the amount of work in trying to fit mixture models. Now, David Cox mentioned about Pearson this morning, and in the sense of being very hard-working and working on well after retirement. Well, in 1894, he had this classic paper on mixture analysis of some crab measurements on crabs taken from the Bay of Naples, and he was trying to improve the fit of the normal curve by using a mixture of two normals. And so this paper was done in 1894. He used the method of moments, and he had to solve a ninth degree polynomial. And so in 1994, I think it was Byron Morgan organised a session at Hamilton, Ontario in Canada on mixture models to commemorate this. And Brian Everett gave a nice talk, and he put up this quote here, which I've repeated, when Chalier was commenting, saying that the solution of an equation of the ninth degree where almost all powers to the ninth of the unknown quantity are existing is, however, a very laborious task. Mr. Pearson has indeed possessed the energy to perform this heroic task, but I fear that he will have few successes if the dissection of the frequency curve into two components is not very urgent. So obviously they could have done with the EM algorithm back 100 years ago. Now, in 1997, 20 years after the DLR paper came out, there was this, I think, this very nice paper by Zhali Meng and David Van Dyke. Meng being a student of Rubin and Van Dyke a student of Meng. And they named it, as I said, this was probably because of the fact that Hartley talked about singing a song. They named it the EM algorithm, an old folk song sung to a fast new tune. And it was read before the Royal Society to celebrate the 20th presentation of DLR. And in it, they basically, first of all, they addressed the issues of the origin of the EM and also ways to speed up the convergence without destroying the simplicity and the stability of it. Because a number of people have sort of suggested ways of speeding up the EM algorithm, but some of the ways of doing it are quite complicated. Now, so I'm not going to say much about the work done before EM, but obviously these were key papers that sort of had some idea of what was the EM about them. And and I mentioned this IBC meeting in 1994. There was a session on incomplete data, and in the session there was Don Rubin, Rolf Sundberg, and Max Woodenberry. I think I can't be 100% sure, but I think these three spoke in the same session on incomplete data, which was really I don't think they've been together really in speaking on the EM since then. Now, Don Rubin was the proposer of the vote of thanks of this paper, and he made this point, and I think I definitely agree with him, that he says that the DLR sparked such popularity in the EM in so many disciplines for a particular reason beyond its numerical simplicity and stability, and the focus of it as a statistical rather than a purely numerical algorithm. And I think because it had this sort of statistical connotations about it, that it was that people, I think, took it up in the context of statistics. On the other hand, perhaps numerical analysts didn't use it because the notion of trying to use data that you can't observe is sort of, I suppose, completely foreign to them. But certainly people in machine learning have used the EM algorithm. Now, people talk about the EM algorithm being slow, and here's a quote from Mike Titterington, who was a seconder of the vote of thanks for the Zhali Meng paper. And he was saying that the EM algorithm really does make good progress initially. And if you're not so much concerned about the estimates of the parameters, but just trying to get a good model fit for future prediction, then things aren't too bad. And so if you look at the cover of the second edition of our book on the EM came out last year, and we had a nice cover on it, but Wiley gave us a few days to produce a new cover, and so this is a poor attempt to try and produce a cover, but here we to illustrate what Michael Jordan was saying and Mike Titterington was repeating, that the EM certainly climbs very quickly after just one iteration, and it looks as if it's converging here in two, but there's a few dots here, but because all the dots came out almost on top of each other. But it does make good progress in the early iterations, albeit it then starts to go slowly. Well, having mentioned books, of course the book by Little and Rubin, and there's a second edition out a few years ago, and the books by Tanner and Schaefer have substantial EM content. Now, as I say, this is a very nice paper by Meng and Van Dyke, and in it they put forward these variants of EM which maintain the simplicity and the stability of the EM algorithm, but it speeds up convergence. So we've got the expectation, conditional maximisation, the ECME, the alternating ECM, and they mentioned the parameter expanded EM that Rubin and Liu talked about in a paper a year later in Biometrica. And so there's not time to run over those algorithms, but if we just look at the ECM algorithm, if the M step looks to be a little bit complicated, then we might divide the parameter vector up into a number of subvectors, for example 2, and then we've got these two, if you like, conditional maximization steps, and on the first one we fix theta 2 at its current value and just maximize the Q function over the first subvector, and then having done that we fix theta 1 now at that updated estimate and then maximize over theta 2. And we can do fancier things than that. We can perform an E step between the two CM steps. So having updated, oh, that should be a theta k plus 1 there, sorry. But having updated theta 1, we can update it in here. And we still preserve the monotone convergence of the EM. Now, I mean, talking about fitting mixtures of normals, people these days have been fitting mixtures of T distributions, skew normals, skew T's, factor analyzers, linear mixed models, and all these variations and extensions of normal mixtures can be fitted with the M step essentially in closed form by using the ECM algorithm or the alternating ECM algorithm. And for example, in the factor analysis model, you've got the observed data vector yj, and then you've got these unobservable factors. Well, if you condition, if you look at the distribution of them, when you condition on the fact that they come from the ith component, if you specify a normal distribution, you can specify a normal, or if you like, you can specify a T distribution. And if you're going to fit the T, that you can, we pull out the scalar variable which we condition on, and then we give it a gamma distribution. And so this characterization just calls out for the EM because you've got these, if you like, missing variables that you can average over when you write down the complete data log likelihood. And similarly in mixture models, in this particular case here, where you're trying to, say in bioinformatics, model the cluster some gene profiles, you've got these fixed effects terms, you've got these random effects for observations on the same gene, but here we've got we let all the genes in the same cluster get this random effect, and we can't write down the likelihood function, but if we condition on these random effects we can, and so that enables us to apply the EM algorithm. And as I said, mixture factor analyzers where where this covariance matrix is highly parameterized. It does the number of dimensions p. As that increases, we get too many parameters here. And one way, if you like, is to use this factor analytic representation of a covariance matrix. We can think of this as a form of regularization. And then to apply the EM algorithm, we write it out in this particular form where we introduce these unobservable latent factors. And then we've used sort of like a multi-cycle EM. So an alternating ECM, and with the alternating ECM, say on the first cycle, you declare the missing data here just to be the component labels. But then on the second cycle, you declare the missing data to be not only the component labels, but also the latent factors. So you can have a number of cycles, and you can vary the missing data, the specification of the missing data. And I think I'm running out of time, so I won't go through all these equations that I put up. But the thing, yes, so this is the point I want to make. If you're trying to estimate, fit a single normal model or a mixture of models using using maximum likelihood, this equation is very unstable. But using the EM algorithm, we've got this matrix here, which makes the thing very stable. So if you like, the expected value of this, the unconditional expectation, is the identity matrix, and you get that. But when you use a conditional expectation, you've got this matrix here, and that makes things stable. Now, I've been given the wind-up, so... I was going to say, because we're in Edinburgh, it'd be fitting to talk about the work of McKendrick, the Scottish physician who was a brilliant mathematician, but an amateur mathematician who didn't receive any formal training. And Brian Everett asked me to edit a special issue of the Statistical Methods in Medical Research on the impact of the EM algorithm. And he chose to talk on the work of McKendrick, and its link to and Irwin's extension of it, which was basically or almost an EM algorithm. And so there's not time to discuss that, but this is a really a fascinating account of the work of McKendrick on this. And basically, this is what you get using the EM algorithm, and McKendrick managed to get almost the same answers. Now, okay, to wind up, how can I sort of summarise the work of the EM algorithm? Well, first of all, I thought I'd take this comment from Meng, who says, although perhaps we'll never be able to find out who really sung the first musical note of the EM algorithm, we all agree that it was DLR who brought it into the all-time top 10 of statistics, see Stigler 1994. Well, I think it almost might make the top 3 now. And he's got DLR made at least 2 contributions. They gave the informative title identifying the E and M step, and secondly, they demonstrated how it can be sung at different occasions, where some of which had not been previously thought to be related to the EM algorithm. So, of course, Meng and Van Dyke aren't at arm's length to DLR, so I thought I'd better get someone who is at arm's length. So, so this is Mike Titterington again. Seconding the vote of thanks, says altogether the EM algorithm has had an extraordinary influence. To look at the citations, well, unfortunately I didn't get a chance to look at the citations in great detail, but in my hotel room the last few days, DLR has got over 10,000 citations in the ISI and about 20,000 citations in Google Scholar. Now, as Professor Stigler said, in this paper in 1994, among the problems encountered with citations are those by Robert K. Merton. There's obliteration by incorporation, where basically, and Meng did allude to this, was saying that when he's trying to work out the number of citations, people were just writing down EM and not giving the reference to it. It had become quite common. There's also the Matthew effect. The Matthew effect, but I don't think Dempster, Laird and Rubin can complain about the Matthew effect. Maybe some other authors might say that they've been affected by it, but certainly this obliteration by incorporation has limited the number of citations. But anyway, this is a table from that paper by Professor Stigler, and but he looked at six. This is back in 87 to 89. He looked at 6 papers in statistics, and Dempster, Laird and Rubin was only getting 85 citations in per year. And I quickly checked last year that it got over 1,000 citations in the year. Now, my last slide. Updating these citations now for this is as of the 6th of the 9th. The Dempster, Laird and Rubin paper has got over 10,000 citations, and of course the paper by David Cox has got the 24,000. A way to lose citations also is to write a book, and this is the book by Brad Efron and Rob Tibshirani. It's got 7,500 citations. So I presume if they hadn't written the book, this number of citations would go up. And of course there's been other books on the bootstrap by Anthony Davison and David Hinckley, and Michael Chernick's got one. And unfortunately, my joint book on the EM algorithms has only provided Dempster, Laird and Rubin with an additional 1,200 citations. But anyway, if you add these two things together, they're still ahead of the bootstrap. So I suppose they could argue they're in the top 3 papers. Well, I'm just taking these 6 papers, and then it occurred to me, well, maybe since Professor Stigler wrote his paper, there could be others. So I quickly checked Gelfand and Smith, because people using MC methods, it's got 2,000. And then I also checked this one, Yoav's paper, which he'll be presenting tomorrow, I think, and it's only written in 95. It's got 5,000 citations already, and given the way people publish paper in bioinformatics and talk about false discovery rate, this is certainly on an upward trajectory here. Of course, it's going to suffer from obliteration by incorporation, and but when you look at this Kaplan and Meyer here with 33,000, I suppose you could say that maybe Dempster, Laird and Rubin should have called the EM algorithm the Dempster, Laird, Rubin algorithm, although that's a bit of a mouthful. If there's only 2 authors, maybe they could have. And they could have. And if they had called it Dempster, Laird, Rubin, I'll leave it to you to draw your own conclusion whether Stigler's law would apply to it. But, okay, good. Thank you for your attention.